Good morning, everybody. Good morning, faculty members, colleagues, and students. I have been given this privilege to introduce Mr. Diptanu Choudhury. So today we have a great opportunity to interact with a great force in AI/ML, who, having worked for more than a decade in this area, the word force aptly describes him. It gives me immense pleasure and pride to say that he's an alumna of our institute. So, ladies and gentlemen, let me introduce to you to the expert for today, Mr. Diptanu Choudhury. Mr. Choudhury has worked on huge projects for firms like Cisco, Netflix, HashiCorp, Facebook, ThoughtWorks, just to name a few. He is also a co-founder of GIS-based social networking system called LifeOS. His expertise lie in the area of AI/ML in the domain of cloud computing and NLP. He has been very gracious and has agreed to share his knowledge with us on the topic of federal learning, privacy-aware AI at the edge. Just to provide a background for our students who are in this session, federal learning is a decentralized form of learning such that data from various edge devices or servers is used to drive analytical algorithms without actually exchanging the data from them, which in contrast from traditional machine learning techniques which are based on local data sets first being uploaded to a server and then they are analyzed. Thus, this technique allows us to address the issues such as data privacy, data security, etc. with applications in defense, telecommunication, Internet of Things, and pharmaceutical sectors. So with this, I would like to hand over the floor, or in this case, the screen, to Mr. Diptanu Choudhury. We welcome you, sir, for this expert talk.
Thank you. I wanted to have this talk be super interactive. Initially, I wanted to do a talk about what is happening in AI and what I'm working on and what is exciting. But it didn't feel like it was going to I had a good plan for it, in terms of the topics that I wanted to cover. And I thought federated learning would be a good topic to discuss because it's interesting, it's relevant to what is happening in the industry right now. Everyone is trying to do federated learning. I think the first paper of federated learning came out a couple of years back, and it's still taking off. It hasn't taken off, so there is a lot of opportunity for research, and there is a lot of opportunity for exploration of federated learning for new use cases. So I thought it might be a good idea to talk about this, especially because you guys are all students and trying to do research, and so I thought it might be a good topic. And I want this conversation to be as interactive as possible, so please stop me and ask questions. I don't have a lot of slides, so I'm hoping you would ask me questions and we can have a good flowing discussion going on.
That's great.
So let's see. How do I do this? All right, can you guys see my screen?
Yes, sir.
All right. All right, so I wanted to do, as I was saying, I wanted to do this talk on federated learning because I think this is one of the new trend in AI, and there is a lot of unanswered questions left, and I think there is a lot of scope for new research in this space. The couple of main reasons why I think federated learning is taking off is AI is everywhere now, right? AI is pretty much everywhere. You see a photo on a social network, there is probably some AI happening. You see an ad on a social network or on Google, there is AI. You ride a car, there is probably AI there, which is like, driving you from point A to point B and so on. And the trend in AI, I think, in the last 10 years, or at least like the last, I would say like last 10 years, has been AI models were served from the server, right? So you had a browser or you had like an app, and then the app would send some data to like an API on the server, and like we would extract features from the data, and then we would run some inference on a model and then respond back. And that was cool because it allowed us to keep the same architecture of applications, right? Where we had clients and then we had servers, and the models being pretty large and the models being pretty huge allowed us to use servers where we could get capacity to run these models. But with like more and more people like accessing the internet from mobile phones, like for example, like my mother, like she doesn't have a computer, she has like an Android phone, and that's all the computer that she had in her life. And increasingly, like more and more people like who are getting on the internet now, like they're probably like using a mobile device to get on the internet. And these mobile devices, I don't need to tell you guys, I mean, they're super powerful. Like they probably have as much or more power. Like my iPhone probably has more power than the first laptop that I bought when I was in college. So it's definitely possible to run more and more models on 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 mobile phones. I don't know if you guys read AI blogs from Facebook or Google. A couple of years back, Google wrote a blog on a new model architecture called RNNT, which is like a recurrent neural network that does ASR, automatic speech recognition, and that ran end to end on phones. And similarly, Apple had AI running on phones, like where a lot of like predictive text that people type on phones are completely run on device. And similar trends are everywhere. Like there are similar trends everywhere, and like that's the new trend where like we are trying to put models on people's phone, and all the new phones have tensor cores. What it means is that there is a special hardware in every phone now, in most phones at least, which can do tensor maths. With tensor maths, like you are doing matrix multiplication and stuff like much more faster and in an energy efficient way compared to like doing matrix multiplication on like a general purpose, for example. And so like a lot of these models can now run efficiently on phones. So that is one trend. And second trend is getting training data is like hard. Like if you have read any machine learning paper, like they're probably like writing a paper and showing their results on a very popular data set. And there are very few popular data sets. Like like for example, the biggest breakthrough in AI that happened, I think in 2012 or whatever, like when the ImageNet paper came out, and ImageNet was a data set on which like people could run experiments and people could test new AI models and so on and compare results. And there are companies built around just making training data now. So if you are starting a new company, like building AI models, like you're probably like spending a lot of money on like acquiring training data. So like getting new data is hard. So for example, let's say like like we want to train like a face classifier or whatever classifier, like based on images. Now on your phone, like you probably have like hundreds of images, right? And some of these images could be like coming from someone's message, or like or of like your friend that you have taken and so on. And so there is a lot of data that are there on people's phones, but they're not necessarily available to train machine learning models on. And even if you want to acquire them, like it's really costly. Third is there are regulations around privacy now. So for example, in Europe, there are very strict privacy laws around, like what data you can access and what data you can't access. Like if someone stops using your service, then you're no longer used to use a model like which is trained from that data and so on. So it's getting complicated to like acquire data, right? And third, I think people in general don't like to share any more stuff like from their phones or their personal information. At least like me, like I don't feel very comfortable like sharing my personal information. Like, I can see like how fine tuning a model on someone's data could be like hard. So these are basically like the trends that sort of like lead us into federated learning. Any questions so far? No, sir. All right, sounds good. How many like sorry, I forgot to ask like something. Are you guys like from? Does most people listening to this like? Do you have like a mostly like a computer science or an AI background, or mostly like an electronics background? Like, because based on that, I might be able to like speak more on a particular topic.
So we come from diverse backgrounds, Diptanu sir. We come from computer science, we come from electrical electronics. We even have people here who have got substantial experience in data science and business analytics.
Oh, cool. Okay.
Already cleared the first semester, and at least we are well past the basic level.
All right, sounds good. I mean, if there is a topic which is like of interest to you guys, like just let me know. Like we can dive deeper. Like it could be like on the hardware side, it could be like on the software side, it could be on the math side. Um, we could dive deeper. Yeah. So the classic algorithm that like that started it all is like gradient descent. And when I was, someone told me that like differential calculus is going to be so much is going to be of so much importance in my life. I would have probably like paid more attention in those maths classes that I did not pay attention. But the basics of AI, I think, like stems from gradient descent, and gradient descent uses differential calculus a lot, which is basically, let's say like you have a convex problem, sorry, a non-convex problem, where you have a function and you need to like optimize the function and find the local minima. Then the gradient descent problem, what it does is it applies all the parameters of it applies all the input to the function, and then it will try to find the slope, and based on the slope, based on whatever the gradient is, it will try to like optimize the parameters of the function so that it goes towards the minima. And classic gradient descent uses all the examples in the training data set to come up with the slope and the direction where it needs to go. Well, direction is always like the local minima, but it comes up with the gradient based on like all the samples. So what it means is, let's say like you have an object detection data set, like an ImageNet or whatever, and every image has an object like a bird or like a car or anything it could be. And classic gradient descent would take all these examples and try to like find the local minima by doing a gradient, by applying all the examples in the function, and thereby like figuring out like what is the slope and where it should move towards. The problem with this approach is that it takes a long time, right? So if you, let's say like you have 100 images, it will take like X amount of time. If you have like 10X the images, it will take like a linear amount of time to calculate the gradient descent. So it's not very practical as we add like more and more data, right? And with stochastic gradient descent, like it kind of changed the game. I think it's like one of those, again, like one of those like breakthrough algorithms which kind of like changed AI and allows us to do what we do today. What it does is it allows us to select like a subset of training samples, and then it runs the optimizer. So let's say like you have 1,000 training data, and you could select like 10 random sample and run the optimizer and calculate the slope and so on. It takes more steps than the than gradient descent, of course, because like you are running it like 100 times now versus like one time in gradient descent. But each of these step, like each of this batch size is like much more faster. Now you might ask like, how does it help? It helps because the hardware on which like we train our models are parallel in nature, right? When you are like when you are programming in C or whatever, like you are the mental model or the machine model of the program is that there is a stack and there is no concept of a thread like in a pure C program, and then it runs on a CPU and so on. But the hardware that we have on our machines are parallel in nature, right? Like there are n number of cores, or like if you have like a graphics card, like you will have like many different cores in the graphics card. So what we are trying to do here is that we are basically saying that instead of running one gradient descent once, we are going to run like 100 times stochastic gradient descent, but we'll also run it parallelly, right? So since each of the step is faster and now we have parallel hardware in front of us, stochastic gradient descent is much more faster and it produces good results, right? So what would take you a week to train on a large data set now takes like very little time to train. Any questions here? Um, so what happens in a classical data center is that we have one graphics card with like say like four, like I don't know, like four graphics card or whatever, like one or four machines with like four graphics card or whatever, and then we are parallelly running stochastic gradient descent on our training samples, and then we have like a master which gets all the data from each of the cards, and then updates the model, like applies the loss function to the model and updates it, and then all the workers in the graphics card then like sees the model and updates the model and so on. Basically, like like in a data center setting, um, you are usually running like a synchronous parallel training, right? And that has worked really well, where the data is seen by all the clients, not all the clients. The data is seen by all the workers, which is doing the training over a large period of time. So the model generalizes better. In federated learning, like what is happening is these workers which are updating the model like parallelly are not seeing the data that are there in each of the other shards, right? What is happening is, let's say like you have like 10 phones or 10 devices participating in federated learning by let's say like we are building an image classifier, right? or not an image classifier. Let's just say that we are building like a predictive text model. So let's say like you are writing, "Hey, how are you doing?" and like the model needs to predict like what comes after that. So let's say like it's 9 a.m. in the morning, you have woken up and you're sending a message to your friend or your parents, like saying that, "Hey, how are you doing?" The model could predict that good morning or whatever comes next, whatever you type, right? Um, so let's say like we are talking about training a model like that. My phone will have like a different training data set compared to like someone else's phone, because like all the text that I am typing on my phone are not leaving my phone, like in the sense the person like who is training the model is not seeing the data, right? um this is like the scenario, right? Another difference that happens in federated learning versus like a regular SGD based learning is that um, the data distribution in an SGD is assumed to be identical, right? So let's say like you can like all the sentences from a Shakespeare's book and tokenize them and prepared like the training sample. You would randomize the data set and you will distribute them equally in all the shards, right? So the distribution of the data like is similar in every worker in the data center, like which is participating in the SGD. Whereas in a federated learning environment, it could be very different, and we call it non-identical. What it means is that if I am typing a lot of texts, then obviously like there is a lot of training samples on my phone versus like someone else like who is not typing a lot of texts and they are using some other mode of communication, right? Um, so the number of training samples and the distribution of training samples is going to be super different. Another difference could be like I watch a lot of basketball, so I am always texting my friends about basketball results, and like we are always texting about what is happening whenever there is a game going. Versus someone else could be super interested in skiing or I don't know, like maybe food. Like people might like food and so on, and so like their communication would be different, and the type of things that their phones are going to see, like the data type of data is going to be different, right? So that is the problem, because in a probability distribute, like the probability distribution of the training data matters a lot in a can generalize, right? Whereas in a if the probability distribution is skewed, then you are not going to get that much generalization in the model. But roughly what happens is there is a shared model in the server that we are going to distribute to all the phones, and then or any devices. It could be phones, it could be like I don't know, like a ref, right? Wherever like an AI model is running. And then each of these devices are going to like look at the training data that is locally stored, run SGD locally on the phone, calculate the delta in the weights between the model that was shared by the server and the model that is now present on the phone locally after applying all the training data, and then the delta is going to be sent to the server. Now the server is going to be like getting all the deltas of all the model, right? And then do an average of all the weights that it sees from all the devices, and then create like the next version of the global model on the server, and then again distribute the same to all the phones and so on, right? Um, so that's like the high level idea, right? So it's super simple. It's like SGD, but it's like federated SGD, right? It's federated SGD, and also like there are some tricks in terms of like how the weights from different devices are combined together, and in some cases it could be averaging all the weights. In some case like you could have like federated atom and so on, and so there is a lot of research going on in terms of how do you combine all the weights from different phones? And this is an area of research, like if you're interested in doing some research on federated learning, compare and contrast like how the existing ways of combining weights from different devices work, and come up with new algorithms and new strategies and so on. All right, any questions so far? So the key ideas, in my opinion, are a couple of things, right? The Fed average algorithm. The Fed average algorithm is the first paper that came out like in this space, and it kind of like started the whole field of federated learning. It basically is it's a very simple algorithm where you combine all the weights from different devices by averaging out all the weights of the parameters. And they did experimentation on MNIST and a bunch of other popular data sets, and they took like an image classifier and an NLP task, and compared and contrasted various hyperparameters of the algorithm and described like how the algorithm works and so on. There was another paper which was followed after this Fed average algorithm paper. It was the compression, like a paper on effective communication, where they compared like how do you make the updates to the server faster, because in a data center setting, when you're running SGD, like you have like a fast network, or like in some cases people are training on the same machine, right? Like where you have 4 workers and each of these workers are on the same machine, so everything is really fast, and they're using like a global memory, for example, or whatever, right? So it's faster in the data center compared to like training on the phone and updating it and so on. So people are doing different things like compressing the weights, quantizing the weights, and so on, like where instead of sending 32-bit floating point numbers, like you were sending like 16-bit numbers, or even like 8-bit or 4-bit numbers. And there are some trade-offs. The trade-offs are that obviously, like when you use like a lesser precision, when you are training, you are losing some accuracy. And then like figuring out like how to add the losses, and then kind of like get to the same loss like that a 32-bit number would give. And then there was like another paper which was really important, was secure aggregation. What secure aggregation would mean is that it was like a protocol, like a cryptography protocol to update the global model on the server without knowing any of the local details about where the model was trained. And lastly, differential privacy. Like there are many papers now where people are trying to reverse engineer PII, personal information of users, from a data set. And differential privacy is a branch of AI, or you can call it a branch of privacy, which deals with figuring out like how you can add some noise to the data set, or add some noise during the training, so that you learn about the trends of the data set and not like individual details or individual examples from the data set. For example, there are recurrent neural networks where we have seen that there are papers which have explored, like the network memorizing some of the data that is there in the data set, which is bad because you don't want someone to get a model and kind of like figure out like details about the data set. What you want the model to know is the trend in the data set on which like it was trained, right? So I am not going to cover like everything, because covering everything is difficult, and also when you use like a framework like TensorFlow or PyTorch, like learning all the details of what is happening on each of these areas like are difficult, and honestly like I don't think I have studied too much in, like, for example, like secure aggregation. Like, I know how it works, but I haven't looked too much details into like the algorithm, because the algorithm is implemented in TensorFlow and PyTorch. So, I don't need to like know the exact details, but I know at a high level like how secure aggregation works, for example. Any questions so far?
Could you explain the differential privacy once more? I mean, what does that entail?
Yeah. So, differential privacy is like, for example, some algorithms, some architectures could have memory, for example, right? Um, if you have like add memory into some of the models, then what would happen is, like, if you train it on that data set, you could reverse engineer some of the examples that was there in the data set from the weights of the model, right? Let's say you have, you train a predictive text model using an RNN or an LSTM, like a long short-term memory algorithm model, and you give it to someone, and like, it uses the data on your phone, and someone reverse engineers the model and knows some of the words that are there on your text messages. Like, that would not be good. So instead, like, what we want is, we want to add some noise into the data, right? So let's say like, we are asking everyone in the class what is their height, and let's say like you add some noise to it, where you add some noise which is like from which is a random where the probabilistic distribution of the noise, which and it comes to like from 0 to 1, and then you add it to everyone's weight, not everyone's weight, everyone's height, and then you teach like a model to like learn, predict the height based on certain parameter of the people in the classroom. Then even if like the model is memorizing some details about some of the information of people, the heights are still going to be wrong, right? Like, the exact heights are still going to be wrong. So
in a sense, it is something like in the conventional computing, we do masking. So we are somewhere doing some bit of masking or randomizing the data or whatever, calling that as adding noise to the data so that nobody can reverse engineer and come to the original facts and figures from the output of the model. Is that what you're saying? Like in RRNs, where you have the model.
Yeah. Absolutely. So there is a bunch of papers on like getting data out of like models, like in the sense, like, if you have an image classifier, like, you can figure out what was the images that they were trained on, and so like, if the model is learning the trends, where, let's say, like in the height example, because it's so easy, like, you add like point whatever, like some you scale the height or whatever, and like the model learns the trends, where the model is looking at the parameters of the students, and it is learning like some incorrect height, where there is like some randomness, where the randomness is controlled. Then the model is sort of like learning the trend in the data set, versus the model looking at everyone's height. So in federated learning, especially because we are training on real data of people and not even collecting, like, not even like buying data, like, it's even important there. And there are papers where people have shown where not doing differential privacy can lead into the model leaking some information about local data. So that's the crux.
Quite interesting. Thank you.
So I'm going to cover like the Fed average algorithm for the remaining duration, and talk about some of the things that don't work well, because I think that's the most important, interesting part. Like these are open research questions, so like you could think about it and so on. So a server would initialize a model that we want to train, and it would create like random weights, like we do like in a regular SGD, and and then what it would do is that it would, let's say like you have like 1,000 devices participating in federated learning. It will pick like a subset of the devices, and then each of these clients of that subset, it would ask the client to update the model, right? And the client would take like a mini batch of all the data that it has on the phone, do a SGD on it, like it's like the server, and then it would send the update to the server back again. The server would look at all the models that it has gotten like for all the clients, and then average all the weights, and then update the model, select another set of clients out of, or devices out of like the larger devices, and it would like send it to them and get them trained and so on. So the key differences here is that in a regular SGD, which is happening in a data center, you have lesser number of devices participating, in the sense that you might have one machine doing all the training, or you can have like 4 devices, like 4 machines, like on the cloud, right? Like which is doing the training. And each of these devices will have a lot of data, right? Like thousands or millions of training samples, right? Whereas in federated learning, it kind of like the inverse. What happens is you'll have like many, many thousands of devices, right? But each individual device would have very little data, right? My phone can have like 10 messages, right? Someone else's phone can have like 100 messages. But if you are training the same thing on the server, you might have like 10,000 text messages that you might have bought from a company, or like which might be available like in an open data set, like a Shakespeare's book or whatever, right? Text is text, like who cares where it came from, as long as like the use cases are similar, right? Or like if you're doing like a sports model, like a predictive text for like a sports use case, you might be like crawling ESPN or whatever, and getting text. But my point is that in the data center, you have a lot of training samples and lesser number of devices. Whereas in federated learning, you have a lot of devices and lesser amount of data per device, right? And the algorithm to combine weights here is like super simple. It's basically an average, and the other thing here is that people have done experiments where the effect of adding a lot of devices to like the pool or the population of devices, like from which like it's going to like do the training, doesn't like plateaus at a certain point. So let's say like you have 1,000 devices or 100,000 devices, and you start increasing the batch of the clients that you want to train at in one shot. The accuracy of the model increases until a certain point, but after a certain point, the accuracy of the model doesn't increase any further. And this is in the paper, like they've shown like how many ever clients at which point like the model starts getting better. So it's super simple, super naive. The cool part of this model is in the averaging part, and also like other hyperparameters, like how many clients you have, how many batches of clients you select, how many how much what are the mini batch size that the model is trained on each clients. That is also like a hyperparameter that you want to like tune for and sort of like learn, and like an area of research basically. So as I was saying, we can summarize federated learning in like 4 steps. First, you select a subset of device, then you send the plan, the execution plan, and the checkpoint of the model to like each of the devices. The runtime on the device updates the model, trains the model, runs local optimization, SGD, ADAM, or whatever like is your favorite optimization algorithm, sends it back to the server, and then the server weights all the average and updates the model and so on. To make it clear, like what happens on the server is like you have a runtime, which is the app process. It could be like a PyTorch or like a TensorFlow or whatever. Looks at the data that is on device, updates the model, and then it sends it back to the server, and the server updates the model and so on. This photo is from this paper called Federated Learning at Scale. Again, I think it's a paper by Google, which is one of the first few papers that they did, and it's been seminal and used everywhere in the industry. One interesting thing for me, at least, was studying the implication of weight initialization. So they did 2 experiments. In one experiment, each of the devices randomized the initial model. So like every device from the population starts with a model that it initialized the model with like some random number, runs the training data, and then sends it to the server. And another example where the server initializes the model, like the global model. So all the devices sees the weights, like some random initial weights, but all the weights are similar. So like if I have a phone and you have a phone, in the beginning, one experiment initialized the model differently in both of our phones. And in the other example, the starting model was the same. The random values were the same. We saw that on the paper that if you mix the weights, then the model doesn't do very well. The loss spikes up, when you average, right? But if you initialize the model on the server, then when you average, the loss dips, right? Which is obviously better. We want the loss to go down, right? Every time like we are running training. So that I thought was interesting. And again, like to drive the point home, like you select a bunch of devices, send the model and the weights to the devices, get the model back, and then you do it again on like a different set of devices. And what is interesting here is that the time it takes for the model to update, like for each of this population, is a long time compared to like what you would see in a data center. But the model sees a wider variety of data than what it would be seeing in a data center, and it converges in lesser steps in some cases, whereas in some cases it doesn't converge. And so federated learning today can't be applied to like all the classes of problems that we see. The challenges in federated learning, I think, to me, like especially like someone who does it at the data center level, is that the probabilistic distribution of data, like the non-IIDness, is a huge challenge. People's data, like the data on every device is kind of like homogeneous, whereas over a large sample, like you see heterogeneity at the population level, and it kind of like doesn't work well with like classical machine learning algorithms where we depend on like randomness. Secondly, the 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 data distribution is unbalanced. As I was saying, some people's devices might have more data than others, and also some devices are faster. Like I have an iPhone, it's a lot faster because there is there is a GPU, there is like neural cores and whatnot. Whereas like a lot of people would have Androids, like, low power Androids, where, there are no GPUs or whatever, or like there is no neural core. This is again, like a pretty big area of research where how do you generalize model across like a heterogeneous pool of devices? Facebook has a really cool paper on it. I recommend, if you're doing AI and if you're interested in on-device AI, read that paper. I think it's called like Survey of Machine Learning on the Edge or something, where they I forget the name of the paper. They act like a survey of like what kind of phones people have and what is the capability of the phones. Like, how many people have phones with GPUs? How many people have phones with like good CPUs? How many phones are there like with with like a neural core where you can do tensor maths? So recommend everyone reading the paper if you're interested in this. And the distributed nature of the problem makes it hard as well. Like you have a lot of partitions. Some devices might not respond. Some devices might respond faster. Federated learning is usually done to preserve battery. So like, when you're not using the phone, that's when like they would do like whatever model update they need to do. So it could be the cadence of the model update could be like very infrequent. So in that case, the server is not seeing data from many devices. And lastly, like limited communication, these are cell phone networks. So like the model updates to the server is going to be slow. So it's going to take like a longer time for the server to get the model update and send and select like the next bunch of devices to run the algorithm on. So that's pretty much it. That's all I had. That's all I had for this presentation. And
okay, so let's open the floor for questioning. I guess you students, Yogenda, you had a question.